We are continuing in 3.2, more concepts of vector spaces. So let's look at basis and the unique combination criteria. So definition 3.6 is the definition for a basis for a vector space. And this was done a little differently in chapter 2, but it I think one was the theorem, one was the definition, and then they reversed it. So in this case, we'll just proceed and go from here. This is the definition of a basis for a subset of the vector space. So you have V as a vector space, and then a set of vectors in V. So you would normally say something like maybe B as a subset of V. So this subset is called a basis for the vector space V if that set of vectors is what? So the set of vectors has to do what and what. There's two things that have to be true for it to be a basis. What are they? So the set of vectors have to create the entire vector space, right? When you do all linear combinations, it has to be every vector in V. So when you think of basis and span, you always want to think in terms of I and J, or IJK. Because the span of IJK is what you're doing to create all the vectors in R3. Same idea. So the set of vectors, so actually, this is what you have to have in your mind, or you should have in your mind, is that the span of those vectors equals the set R3. Okay, so in general, though, the set of vectors have to span V, and they have to be linearly independent. So you don't want like repeated vectors in there. So the set of vectors is linearly independent. And these are abbreviations, of course. Okay, so the next theorem we're going to go through and prove. It'll take a little while, the rest of this video, but it's a good one to go through and see if you can understand it as we go. So, and I like to often write down the theorems so we can discuss and you can see how it is being set up as you go and write it down. It helps the learning process. So we're going to let V be a vector space. We're going to have, or let, be a subset of V. So B is a subset of V, and B is not made up of all zeros. So just not all zero vectors. So it basically, it isn't just the zero vector, basically. It has to have other cases in there. All right, so then B is a basis for V if and only if for any V in V, so when you just say it like that, it's just arbitrary. So for V in V, the vector V can be uniquely expressed as V equal to, so the linear combination, but it's uniquely expressed like this. I'm going to have to bring this over here. So uniquely expressed as R1 B1 plus R2 B2, etc., to R sub K B sub K. And then those are scalars. So for R sub I in the reals and the b sub i's in B. So this is unique. The whole point of this basically is that this is a unique linear combination of these vectors. So the r's are unique to create your V. Okay, so let's take a look at this proof. I was looking at something else. What else was I going to do? Oh, that's okay. All right, so here's the proof of it. So we're going to, you have an if then and then an if then. So if B is a basis, then V is uniquely expressed like that. And then you have vice versa. If V is uniquely expressed like this, then B is a basis. We are already assuming here